So here we're going to talk about springs. There are many types of springs. You got springs that are meant to act in compression. There are springs that are meant to be act in tension. You can have springs in cars, in your mechanical pencils, in airplanes. Basically, everywhere you can possibly think of, you're going to have a spring. So in this lecture, we're going to focus our attention to the helical compressive springs. So those springs that are meant to act in compression only. So as we start the discussion, let's consider the following case. Like for an example, we can, as I just mentioned to you, you can have a mechanical pencil. You got the press pistons. So example, the pistons, you can see they're actually inside a cylinder. Same thing, these springs actually both ways. They are inside the cylinder and also inside over a pin. So basically, given a load P, we are trying to find what the diameter D is going to look like to accomplish this. So you can see the springs here. You can spray these springs here. Another example like the shock and servers and these pins here, right? And you can see that it's the same concept. You want to have a load P and you want to find the pin diameter, the maximum possible pin diameter to hold the springs intact. Okay, so this is, you can see the springs inside here. They're actually wrapped around the pin and the shocks as well. So basically we want to find this wire diameter, and the wire diameter is going to come from your table A28, and this list is just a sample. You can keep on going this table. Let's suppose I want to work with gauge number 2, right? So then you have gauge number 2, and then what you will do is you will just go along this list and you will find which type of wire diameter you want. So let's suppose I'm working with steel, right? Steel wire. This is the most typical one that we work with. Then you can see that the wire diameter will actually equal to this. And if you're doing iterative process, you just start at the diameter here. You can go gauge up, gauge down, depending on the case that you're working on. And the way this really works is you have a really big long wire, and this long wire has a length L, and this length L actually has a diameter D. This diameter D, with the diameter D that you found from the tables, then you just go this and you wrap it around to get the effect that you're really looking for. Let's just show you an example of what I really mean by this. Let me show you a small video. You can see how they cut the wires. You can see right here that they're actually wrapping this around how the ear is actually built. We got the machinery to do that. And we got many different applications. So this is one company that does these, right? You can see how they actually give heat treatment, sometimes with heat treatment, cold treatment, different type of treatment. Sometimes they paint them. This is called, what they just did there is called pinning. Okay, it's pinned because they actually help with for rust purposes, but actually takes away the life of your structure. So this kind of gives you an idea how your diameters really work and how they're actually built. Okay, so a couple definitions that we have to we should define before we move on. When we spoke, small d is the wire diameter that we just spoke about. The capital D is nothing else than your mean coil diameter. Okay, so this is the mean coil diameter, and is given by your capital D. This right here is given, is called the pitch, and it's the distance between the center two consecutive coils. typically all your springs have the same pitch. Rare that you have a spring that doesn't have that. And your C is a spring index C. So the way spring index C works is a capital D, your mean diameter divided by the wire diameter, and has to have a value between 4 and 12. Your book doesn't say that, but it's very important to keep that in mind, because anything below 4, it will be very difficult to manufacture, and anything above 12 is very prone to buckling. So just to avoid that, when you start your design, you should make sure that your design is between these two values. And how does this work? Well, this works is, well, you're going to have an initial D as a guess, and that guess is going to come from this table. Okay, any gauges from the table, don't use arbitrary number, just go for the table itself. Then you say D is equal to C times D, so now you have this. Or sometimes we don't have the C. So if you didn't have that, typically start with an initial guess of 8. 8 is acceptable. And then from this, you have 8, then you could find the dimensions that you are looking for, okay? Either dimensions. So a typical range, we know that I told you your C is typically the extreme value is 4, and the extreme value is the lower end is 4 and the upper end is 12. However, typically 6 to 10 is very common values that we like to use when we are designing springs. Okay, there's a handout, by the way. It's posted online, so you can download the handout and follow the handout as well. And then there are a couple of dimensions that you have to keep in mind. These are things that probably your book doesn't talk about, but they are very important in this discussion. One is called the spring outer diameter. Spring outer diameter is this diameter here that goes from here to here. And as you can see that the dimension here, this is D over 2, because this is the wire diameter, is half of this. And then here as well, you're going to have D over 2. So your total D, the dimension of the outer diameter, will be the inner diameter plus D over 2 multiplied by 2. That's why this is given by this value. And the same thing if I'm talking about the inner diameter, what's going here on the inside, this diameter right here, then that will is given by D minus the mean diameter minus the wire diameter. Now, if you want to design what the dimension of your pin or the hole diameter, that's basically typically because of manufacturing tolerances and what we typically use in the industry. This is given by these values. Okay, again, this is not in your textbook. This is given in the handout I gave you, but it's important, and you will be designing using that. But that's what we really do. Okay, so the couple other dimensions that you have that I would like for you to keep in mind. First of all, think for the case of free length, right? Free length is this is out of the package, out of the box. This is you take it out of the box, and this is what you have. But you never use the spring like this. You need to apply a preload. You need to apply a preload so you can everything can be engaged. Okay, and this is what we call the assembly length, and I'm going to call the letter LA. Then I'm going to call the minimum working length. This is at the maximum working load. So this is Y is work. And then this is Y clash. Y clash is what happens when you are actually completely compressed and this is completely shut. There's no spacing left between one coil and the other. And this is a very important design because you don't want your coil to break when it actually slams up together. So a typical value, we can take 0.15 for your design. However, it's very common that you have 0.12. 0.12 is very common and 12% as well. But for design purposes, 0.15 is good. Okay, and then obviously it's bound by 0.1, 0.10, and as high as 0.15, but never go outside these values. And then what you will have here so these are the different range, different dimensions that we have. And for the preload, in case, if you want to know what your initial preload, this initial preload is, there will be nothing else in your initial load. This is typically known in the problem. It comes from design, from the manufacturer. Manufacturer tells you what this value is divided by the stiffness. Stiffness is given by the manufacturer, and we can design it. Okay, and for our purposes, this would be F minimum, okay, divided by K. This is your preload. Okay, and then your working load, this right here, will be nothing else than Y work would be F max minus F minimum, again divided by your K, and this is typically given. Okay, so many times, or it's very common that this delta work is given to you. So you typically know this. Okay, this one is typically given in the problem. Okay, a couple of dimensions that we just keep in mind here. This is called the free length, can be found by these equations here. Um, and just note that this everything that we are doing is we are talking about linear springs, not a nonlinear spring. So if I'm saying I have y initial, well, that's also going to be related to some f minimum or f initial, and we have a slope k. This is load, and this is your displacement. So this is known in the problem. Okay, this is curves are known typically from the problem for every spring that come from test data. And then your assembly length can be found by any of these equations. And by this equation is L sub 0 minus the initial. Your minimum working length would be the L work minus this, the free length minus LA minus this, or initial minus work. And LS is completely a shut, is the subtraction of all the loads minus the clutch value. Okay, and note that this value right here actually comes from tables. Okay, and I'm going to talk about that in a few minutes of what value, what tables we are talking from your textbook. So let's continue our discussion. We also have something we call the spring deflection. So, and I'm going to tell you where this term comes from later. But right now, your y is given by this, and typically this number is very large. So this is actually almost close to 0. So we can ignore this term, and that's why you find this typical expressions that we use in many different textbooks and different variations depending on the case and depending on what you really want to design or do. Okay, so if what you had was your mean and your wire diameter, this is maybe a convenient equation. If you had the index and the wire diameter, it may be the convenient expression. If you had the index and the mean diameter, this may be the convenient expression. They're all equivalent. You can derive them using the fact that C is equal to D is equal to mean diameter is equal to the spring index times your wire diameter. Okay, and just this comes from your G comes from the tables. Just note that from the tables itself. This is your shear modulus, and so it comes from this table right here, table 10.5. And just note that for an example, I'm working with high spring or different steel with stainless steel, And many times when you don't know something and it's steel, typical value for steel is 11.4, maybe 11.2, and that could be just acceptable. And note that this is MSI, so multiply this to 10 to the 3 to get KSI. KSI is a common value that we will be using. Okay, don't forget this. Okay, these are the values that we're going to use. We're working in English unit, and these are the values that we use. We're working in metric units, and then they have values of tension and compression, and some have dimension, the wire diameter criteria for this. Okay, so that's where this is going to come from. And then just note that many times we also express this whole thing by F divided by K. So if I just took this F and I brought, let's say, the first expression and brought everything at the bottom, you can show to yourself this is equal to, you can express it as follows. And this, sorry, this is your K. Okay, this is the spring stiffness of the problem. Okay, so let's move on our discussion here. So the spring rate, and assuming the spring has a linear behavior, as I just mentioned to you. So let's suppose I have a spring, okay? And as this again comes from your notes, you can make a pause and take notes on this. So basically what you really have in the problem is you have a linear spring, okay? It's completely linear. So you're gonna have, this is gonna be, the working is never from zero. You're gonna start working at a preload that's F minimum and Y initial. And then you will have another load up here that's gonna come here. This is the maximum working load, Y work. This is F max. And yes, you could, yeah, you typically we don't draw this in the plot, but you could also have your F shut, right? This is what happens as shut. This is the extra class that you actually add there, and this will be Y add shut, okay? And then typically what you have is your working load is there. So for a load F, you can find your Y. That's what you're looking for. And then between these two values, this is your working load typically. This is your delta. Your delta is given in the problem. Your workload is given in the problem. And just remember your K. Your K is also equal to this value. Many times you have your K, many times you don't have it, but you know that you can find K from here as well, but many of these dimensions are probably known, so you can iterate from here and go back and forth, okay? And don't forget, this is preload, okay? Sorry, this is K, you can get it from here. Okay, so another item that you keep in mind when you're doing this is the number of coils. These are, again, different type of, these are how many coils will be active in the problem. And that's important because you can have the whole spring, you can have lots of coils, and the coils are nothing else than you count this, right? 1 coil, 2 coil, 3 coils, 4, 5, 6 coils. So those are number of coils, okay? So how do you find that? Just keep in mind that you want to bring this to the nearest 1/4, and the number of coils have to be between 3 and 15 in your design. So let's say, for an example, your coils will, what I mean by nearest 15, or 1/4, if this is going to be 925, 950, 975, etc., etc., etc. So let's suppose I had a coil of 9.18 Na, right? So the Na you will choose is the next up. If I had a coil, let's say 9.53, then you choose the one to 9.5. Okay, so this is how we actually work in the coils. And this is important also to keep in mind that this is going to depending on this number of coils, this is also going to can affect your design as well. And how do we find those values? There are a couple of things that your textbook has. First of all, is the right hand, and this is the left hand. Right hand, left hand depends on the direction. So we say right hand, you see how this is actually is rotating in the opposite direction. This was wired in the opposite direction. That's why you see these are different, okay? So, and the solid lengths and everything that you're looking for, that's going to come from your next slide. Okay, so that's going to come from this slide over here. This chart here is going to tell you, depending on the end, the type of ending of your coil. This is the very common one, the most conservative one. So nothing is given, just design it for this. So if I want a total number of coils, it's actually given by this. See, if this was the case I was working with. And if I have the total number of coils, you see I can find my solid length. It's given by this. If I wanted to know what my free length is, and this is related by this equation. The pitch is given by this equation. They're all related here. So don't forget your L sub 0 is nothing else than Y total plus LS. Okay, that's a nice equation to have. But this comes from your table from your textbook as well. Okay, so as we move on, a couple of dimensions here, just to, it's best to see examples. Your free length is important because we're going to check buckling for that, so you need to know that. Your pitch angle, if you have those coils, right, your coils go like this and like this. So then the angle that's formed here with the horizontal, that's actually your pitch angle. That's what we are evaluating, and that's the equation for your pitch angle. The total number of coil, the total coil length is, if I took this wire, right, and I was going to stretch it completely, and that complete stretching is what is I'm talking about LT coil. Okay, that's the total coil that I'm going to use. Okay, active coil length, well, it depends on NA. Okay, that will be the how much, maybe only this portion of your coil is going to be active. The rest goes to your end fixity. Okay, so this is ALC. Okay, this again goes back to related to this table that I just discussed with you. Okay, so there are a couple of more things that we have to know. Now here we need to find your ultimate tensile stress. The ultimate tensile stress, this is important, is going to come by two parameters. You can use your A, B, and M. This is your wire diameter. This is your wire diameter. These two numbers here, they come from the next table. And I'm sorry, there's a minus sign. If I write it like this, you have to put a minus sign, or you can write it like this if you don't want the minus sign. Okay, so these values come from tables. They will come from the next chart. They will actually come from this particular table here. You can see, depending on different cases, you have the value of A here. The value of A here, and your value of M, that's the exponent that's given here. So depending on the case that you're working with is the case that you actually use. Okay, Then once you have those values, then from here, you will find this value, okay? Then you can find what your ultimate tensile stress is. And this is a very important value that you need to find, because from here you can find allowable yield stress, shear stress. The allowable yield shear stress is given by YS. Some textbooks use SY. I use here YS in our convention. And what number goes here, it will go using this table. Your textbook has this table, but this is expanded. And so I recommend you using this one. These are the values that actually go, that number goes inside here. So if I tell you, give you a different value, and I say has 48%, right? The ratio is 48%, then you know this value will be 0.48. So that's how these values come out. Again, come from testing. And those are the numbers that you will place in here to find this value. Okay, so that's important. Then before we start any problem, remember you have to apply in springs a minimum design factor of 1.2. That is a must and should be given in the problem. So you start with applying the load, you multiply by the factor, even if nothing is given, you want to apply this. This is a must, okay? If I say I want to add an additional factor, if I wanted to add an additional factor of 1.5, let's say, then what you will do is you will actually multiply 1.5 times this. Okay, that's how we actually do these problems. So multiplication problem, so that will be a new ND. That's how we will actually calculate this. Okay, we multiply many factors, and we find your design a design factor for analysis. Okay, so if we took to find what your tau we will use in your problem, and I took a small torsional value there, right? And now in the problem, again, just looking at the critical point can be here at the corners, right? Because I have shear. It's not the top and the bottom because I don't have a moment. I have a torsion. Okay, these are the 2 points I'm using. This is going like this. This is going up. My torsion is going this direction. So you can see that I'm actually using this point right here as a critical. Okay, and your tau max in this problem then would be TR over J plus F over A. Okay, so that is, and then given that value, you can actually show that the value that you use is pi d cubed plus 4 times F pi d squared. Okay, and we keep on moving. I know there are lots of equations, but just bear with me for a moment here. Then when we add these, then we find this famous factor that I told you earlier that we will discuss later. Now this factor, we're going to get rid of this factor and we're going to multiply a factor k. So even in the deflection, if you wanted to, you could use that factor k if you wanted to add to that. But it's not really necessary. But now for shear, it is. Okay, so if you are only using shear correction, then this value that I have here, that will be correct. Okay, if you are only using, you're using both shear and curvature, then any of these two values are correct. Your book likes to use this value, and it is very conservative, and it's acceptable. So and this is the value that we will use in this course. Then if you only wanted to do a curvature correction, your curvature correction, it is the dividing KB divided by KS. For the conservative analysis, we will use the largest of this, and that's what we're going to use this analysis right here. Okay, so just keep in mind that so that's why your shear has to be multiplied by this load factor and for different values of C or spring index. Okay, so the couple of things that you keep in mind when I'm doing preload. Again, you need to always check. One check is that what happens at preload. This was already calculated right here. Remember, okay, you calculated this. Okay, so now use that and divided by I, and this I is given by this equation that I have over here. And one thing that's very, very useful, just wanted to point this out here, for value is equal to 8, that's very common, is a good value to have in handy that this is 1.17. This is very common, so the value 1.17 becomes very, very useful. Okay, so this is how we will find this value. And then if I'm looking for the maximum working load, is T maximum is right here, is at work. And so this is the load that I will actually be using here, okay? And this always, as usual, as we always, do this analysis. So you will not only do this at the working load, you also have to check what happens at shut. Okay? At shut, you have to do a couple of things. You need to find your L sub 0. You need to find these dimensions from table 10.2 or calculate them. Find the displacement at shut. You need to use this equation. And then to force a shut, because you only have your spring stiffness, and find your shut, force a shut. You have to find your stress, F shut that you just found it here, and make sure this is all bigger or equal than 1. Remember, your loads are already multiplied by 1.2. Okay, that's important. So note that my check number one was strength. Okay, we already did the strength check. Check number 2 is stability. You want to make sure your springs don't buckle. Okay, but to find your critical load, what you will do is your critical length. You can use any of these equations. This is your Poisson's ratio. This is general, applies for everything. This applies only for steels, and this is since most of us steels and square ground ends, this value becomes very handy. Okay, but you may wonder what values do I use? Well, the values you're going to use come from table 10, come from this table 10.2. These are the values of alpha. You can see that if both ends are pivoted, alpha is 1. If they're one end clamp, one free, alpha is 2, and etc., etc. Depending on the cases you use, that's the value that you use. Again, this is very common because most of our springs are steel, and since most of them are ground ends, this value becomes very handy. So what do we do with this analysis? Well, then once we find the L critical, depending on what, if you can use this, or you can use this, or you have to use this, then you make sure L sub 0 is less than L critical, and your L initial plus working is less than L critical. So this one ensures that it's not going to buckle at free length. Think about, you open from the package, you put it on the surface. You want to make sure that this doesn't end up buckling, right, without the load. And this one is going to ensure that once you have the full load, right, you apply the full load, the maximum working load, this is not going to buckle either. Okay, this is not at shut. At shut is not going to buckle because all the coils are piled up against each other. So this is all for the analysis of static. This is mainly static analysis, the only theory related to static analysis.